Morning, everyone. It's a pleasure to be here. It's a lovely city, and this morning's weather, at least, is lovely. What I'd like to talk about today is this interaction between scientific ideas and telescope design, which has always been one of the engines that moves our science forward. By way of overview of my talk, let me say there are going to be three science themes I will talk about, and three telescopes. But these telescopes overlap in their connections to the themes, and as you will see, I will artificially thread each one to one of the themes, but that's only for convenience. Per the request of the organizers, I'm talking about things which are on a 20-year horizon, so these things which are likely to launch in the 30s. I should say, by way of acknowledgement, that a lot of these ideas have been worked up by many groups. I acknowledge borrowing and stealing material from them, but by the same token, I should also say this is really my take on the story. This is not an official line by any means from any of these studies. And I should say the studies are supported by various organizations, including NASA and ESA. It's hard to give a talk on telescopes without going back to Galileo. The freshness of his vision remains today a driving force, which is this very simple notion that you can't trust some. So I'm now going to offend someone in the audience. You can't trust the theorists to tell you what's out there. You really have to go and look for yourself. And that's the essence of his thought. And with that in mind, he started this revolution with his telescope. I love this picture. It shows one of Galileo. It's a model of Galileo's telescope. And through the window, you can see the Hubble Space Telescope. I doubt that Galileo would have dreamt up the Hubble. On the other hand, it would have taken him long to realize that it's really a descendant of his little invention. After all, he did make 2 or 3 models and try to improve on it. So he knew already that we were on a path to bigger and better things. So with that in mind, let me introduce the 3 themes which will recur during this talk on the science. As you all know, in astronomy, we boil it down to asking some very simple, engaging questions that are engaging at the human level. And questions such as, how is the universe held together? How did the universe get to its current state? And are we alone? For the first telescope project, I'm going to pick out the "Are we alone?" question. If you had a choice of how to address this question, what you'd like to do is find a few dozen habitable zone Earth-like exoplanets orbiting sun-like stars. As you know, we have no lack of these. We have no lack of such objects, but we anticipate having a lot more of them in the next few years. And the important thing here is that this exercise is all about statistics. Once you found these objects, you want to separate their light. This is the challenge of light suppression from the star, and then analyze the atmospheric emission spectra for signs of life. Once you have done that and you've tallied up how many atmospheres do reveal signs of life, you just do simple math and you estimate the likelihood of life given habitable zone conditions. And the telescope that has the ambition to do that has been proposed under the name of High Definition Space Telescope. The vision is this is a 12-meter telescope for the UV to the near-infrared range. The most important point is that you motivate, you sort of pin down the 12-meter and the technical needs on the notion that you've got to do something like 50 cases to study them, 50 targets, and with 12 meters, given today's state of knowledge of exoplanets. We anticipate that will give us between 20 and 70 Earth-like, Sun-like systems to look at, and so that gives you a sense of the statistical game we're playing. I think with time we're leaning towards more of these objects being available, so that's but that's the driver. But having done that, having built a system that allows you to do this, you have a tremendous payoff in other kinds of science that you can do, from high-resolution images of galaxies to cosmic gas flows, spatially resolved studies of stellar populations and all kinds of environments. The key instrument here is the coronagraph in order to be able to suppress the light from the star and do the spectral measurement. However, a telescope like this will carry imaging and spectroscopic instruments. I won't go into the catalog of all of the things you can do. Just imagine you have a telescope which has five times better resolution than Hubble and 100 times the sensitivity. I will just point one thing out, which is the astounding spatial resolution that this allows you. And I'm going to point out just two things on this diagram. This diagram just talks about the further out you look. Of course, for constant angular resolution, the larger the size of the object you can resolve. And I'm going to point out these two cases. What it's telling you is that you can image anything, anywhere in the universe at a resolution of 100 parsec or so. And this other interesting point, which is that anywhere in the Milky Way, you can resolve things at the 100 AU level. And just to bring it back to the anthropic scale, 100 AU is less than the distance that has been traveled by the Voyager spacecraft since we launched them. So the design elements for this telescope are a segmented deployable filled aperture mirror, building on HDST heritage, very accurate wavefront control. You need, and of course it's UV to near-infrared non-cryogenic optics, the diffraction limited performance, and the key here is a very high stability mode to allow you to do coronagraphy and do the experiment. That is probably the most challenging of several challenging aspects. This lists the capabilities and where the challenges are. Of course, a segmented mirror of 12 meters is already a challenge. But again, the precision that is needed of the order of picometers in wavefront error control to be maintained over 10 to 20 minutes in order to get you to the 10 to the minus 10 contrast. Okay, so chapter 2, into the invisible. Now, 2 centuries after Galileo first introduced the telescope, William Herschel ventured into the invisible. And it's always been the case that stepping off of the visible light was really all about sort of engineering and technology more than intuitive development of instruments. And in 1800, good, reliable, consistent thermometers were good technology. And that's how Herschel discovered the infrared. And I doubt that he would recognize any of these telescopes, this incredible infrared collection of telescopes, as descendants of his thermometers, but this is what we've had over the past 30 years, and we continue to use Spitzer today and WISE. Herschel would be pleased, however, to have probably the premier far infrared telescope to date named after him. And of course, the future is still very exciting with the near-term launch of 3 amazing telescopes, HDST, Euclid, and WFIRST. So back to our themes. For this one, I'm going to tie the development to the question of how did the universe get to its current state. And what we know about the universe is that we know in broad outlines the rough times when galaxies started forming, when structures started forming, but we also know that when this started happening, it was a very patchy operation. It really mattered as much where you were in the universe as when you were in the universe, as to what is happening. And so it's a very, again, statistics are a very important part of understanding the universe. And the other thing to keep in mind is that when the first galaxies were forming, they were being formed out of collapsing gas, which was primordial, unenriched, very different from today's gas. So if I wanted to go out and answer this question, how did we see the first galaxies come about? What I'd like to do is find when and where the first dark matter halos caused gas to collapse into them. So the way I do it is I'd look for molecular hydrogen lines, because that's the main coolant in that era, from shocked gas. We have local analogs where molecular hydrogen lines are remarkably dominant in cooling gas which is shocked, even when the gas is enriched with metals. And we'd look both for single objects and for statistical signals, and what I'm looking for is something on the order of 10 to the 8 solar luminosities in the redshift 8 range, which is in the middle of the era of reionization. And that would appear as a 10 to the minus 21 watt per square meter signal, and this telescope would do the job. This is the infrared deep universe space telescope. The vision is a 10-meter telescope at L2 to operate in the far infrared, 30 to 500 micron. Again here, it is sized to be able to detect this early collapse of gas into dark matter halos, but once you have done that, it pays off in studying the rise of metals, the star formation through history, the relation between star formation and AGNs, the planet formation today, which is very important, and the approach to the coldest phases before stars form in today's universe. You'd be favoring spectroscopic instrumentation on this telescope in resolution which can be as modest as 300. You can do great things with that, all the way up to 10 to the 4. And the line sensitivity, as I said, is for such a telescope is estimated at 10 to the minus 21 watts per square meter for a modest integration. Again, for those who have used Herschel, just imagine 3 times the resolution and more than 1,000 times the sensitivity. As I said, you can track the rise of metals. You can track in particular the rise of dust, which is the first movement of the universe towards solid matter, towards planets as we know them. As an example, you can pick out polycyclic aromatic hydrocarbon signatures at a redshift 6 from objects which are pretty common at those days, in that era. The design elements, you have a filled aperture, diffraction limit of 30 microns. The challenge is in actively cooling it. You'd like to get down to 4K or so. And then you have to cool the detectors, but that we have done before. The sensitivity of the detectors themselves is challenging, but there have been many sessions in this conference on TES, transition edge bolometers, and kinetic induction detectors, and we're on our way actually to achieving that. The technology requirements, the challenges are in getting those detectors not just to that sensitivity, but also get them in arrays which would enable interesting instrumental configurations. The large optical cold primary, you have to be able to do verification and maintenance of figure, and then active cooling of such a large beast. This artist's impression shows that it's sitting at L2, and you still have to figure out how to package and launch this this monster. So the third chapter is going off the spectrum, and I think hardly anyone in this room doesn't know what I'll be talking about. When you talk about how is the universe held together, you're talking about the canvas on which the universe evolves. You're talking about gravity, and of course the fantastic achievement of advanced LIGO with the detection of the first black hole merger, and the continuing work is just unsurpassed. And so the kind of questions you'd like to ask are, how well do we understand space-time and gravity? So far, advanced LIGO says we understand them very well. How did massive black holes come about? What is their growth and merger history? And how does it connect to the history of star formation of their host galaxies? And then what gravitational signals can we pick up from a very early universe, and what do they tell us about that era? The telescope, quote unquote telescope, to answer that is the Laser Interferometer Space Antenna, or LISA. And the vision is that you put 3 spacecraft. They are at the apexes of an equilateral triangle. They're about 5 million kilometers apart, somewhat inclined to the ecliptic plane in an orbit not unlike the sun's orbit. Each spacecraft has a free-falling proof mass, and you do all of your measurements on this mass, and then you use laser interferometers to pick out slight changes in the separation between these proof masses which signal that a gravitational wave has just gone by. The sensitivity that you're looking for is expressed as the gauge of 10 to the minus 23, which means that you'd like to see changes in that, in the 5 million kilometer separation on the order of 10 to the minus 23, which works out to about 10 to the minus 4 picometers, but I'll come back to that in a second. So the difference between advanced LIGO and LISA is simply the frequency, and that's set by the baseline. And with the lower frequency that LISA will pick up, you're sensitive to black hole mergers, which are on the order of tens of thousands to millions of solar masses, whereas the advanced LIGO detected objects which were tens of solar masses. A couple of really interesting things about gravitational wave detection is that the signal fades as like 1 over the distance from the source, unlike what we're used to in electromagnetic radiation. So you can actually see in a certain class of mergers, you can see all these mergers going all the way back to redshift of 15. The other interesting point, one of the many interesting points about gravitational waves, is that once you've measured the shape of the merger signature, you can actually, from that, deduce the luminosity distance to the source. And then you have to chase after finding what the redshift is or what the object is, but it simplifies things tremendously. So, of course, the better the signal to noise, the better the localization and distance. And again, because of the frequencies it picks up, LISA is sensitive to gravitational wave background from the universe when the universe was at temperature, which is given here in TeVs, which corresponds to well under 10 to the minus 10 seconds after the Big Bang. And in that era, the candidate sources are interactions during primary phase transitions, which would have brought out what we now see as the laws of physics that dominate in the universe, and other exotic things like cosmic string cusps. Technology requirements for LISA, as you can imagine, are non-trivial. So you're looking at picking out these variations, 10 to the minus 23 of 5 million kilometers. That still works out to 10 to the minus 14 meters, which is 5% of a picometer. You don't do that instantly. The design is such that if you can watch those variations in real time at the roughly angstrom level or sub-angstrom level, and you can maintain that accuracy, then you integrate over a year and you get down to effectively the sensitivity that you need, which is the 0.05 picometer. The interesting thing about these very massive black hole mergers is that the signal should be picked up and should be trackable for a year or longer, and that's what allows for this experiment to work. So that is probably the most challenging, but as a simpler challenge is that the proof masses have to remain free-falling inside that cocoon provided by the spacecraft. And that has to be maintained, the spacecraft has to be maintained away from the proof masses at 10 to the minus 9 meters per hertz. Okay, so this is my last slide. So I spoke about these 3 science themes and the telescopes, and let me again stress the overlaps in the sense that each one of these telescopes could address several of the themes and many more which were not listed here. In fact, in a supervisionary world, you'd like to have all of these operating at the same time, and the synergies between them would be absolutely fabulous. These telescopes offer very complementary approaches to what I hope you perceive as much as I do as compelling science. But of course, each one of these telescopes presents tremendous technical challenges, and SPIE, I guess, is the place to talk about what these technical challenges might be and how they might be faced. So with that, I will stop and turn it over to the chair.